today, our asset managers at utilities and industrial customers and so forth have lots of challenges. We're trying to manage a grid that we're dealing with global warming, recovery from COVID. As the prior presenter talked about, having qualified employees is a difficult thing to come by these days, and you want to definitely make sure that people are working safely and doing the right things when it comes to working around electrical equipment. So with severe weather events, carbon neutral goals. So one of the things that I know, I've talking to different utilities, a lot of utility folks are installing backup generation at their houses because they know as all these big coal plants shut down and these big rocks that are keeping the system stable are going away, there's definitely concerns about system stability, and now we're running power in from lots of remote areas where wind and solar are located, and so we're all charged with ensuring the reliable electric grid. Then in addition to the generation issues with adding lots of distributed generation, wind, solar, so forth, we're also adding a lot of electric vehicle loads. So I saw a presentation recently that talked about in California where they're adding 1,000 electric vehicles a day. And so those kind of things certainly are putting a lot more stress on the grid than we've had in the past, especially at the distribution level where, most people have focused their efforts on ensuring reliability at the transmission level. But as we move forward, there's a lot more emphasis on ensuring reliability at the distribution level. So, of course, the reliability or the renewable energy, and and as the prior presenter talked about, the supply chain issues. So how long will it take to get you a transformer? And so no matter how much help we need, we're all here to help. And we want to, one way or another, we got to make sure that the lights stay on. So go to the next line. There we go. So today's transformer challenges. So today what we're seeing is, depending on the size of your transformer, 1 to 3 year lead times, 2 to 3 times the prices, aging transformer fleets. And so one of the things that Tony knows a lot about is statistics on transformer reliability, and so transformer failures and so forth. And so Doble has a lot of good information on that. And but the question that we'd like to pose is, how much does age really matter? And so Tony's got some good information we'll go through here in a little bit. And again, additional load from electric vehicles. We're hearing from customers that the inverters on the solar panels are creating harmonics that are causing transformer issues, including failure. And so there's a lot of questions about how well will the residential transformers that are in your neighborhoods and so forth, how are they going to survive the solar panels and the EV charging, and what effect are these things going to have on those devices that weren't really designed for those loads and so forth. And so the harmonics and so forth at the larger solar farms, we're also seeing issues with the transformers. So what effect do all the new devices being added to the grid have on the existing equipment out there to supply the power and keep the lights on? And so, Tony, you want to talk about this one, or?
I'll let you start on that one. It's one of your favorites.
Okay. So This graph is actually what inspired me to want to put together this presentation, and as I was putting it together, I knew Tony had some good information, so that's I asked Tony to join me, and he provided a lot of good information. So if you look at data on how long your transformers are going to last, a lot depends on where you're getting your transformers from, the specs that are used, so forth. And there's not really a whole lot of data out there that is available on a broad basis to show in general how long your transformers are going to last. When I was involved with the IEEE C57104 2019 IEEE guide for DGA and mineral oil transformers. They surveyed, or they had data from about 1.4 million oil samples from over 300,000 transformers. And so this is the largest data set that I'm aware of, and maybe Tony Doble has more, I don't know. Probably not. But
yes, we do.
Oh, okay. So Doble does have more. So again, why I had Tony on. So but the interesting thing is, if you look at out of the 300,000 transformers that were in the IEEE data set, you notice that most of the DGA samples are being performed on transformers that are in the 5 to 20 year range. And after the 20-year point, you start seeing a fairly rapid drop in the amount of samples available from transformers that are 20 years and older. And so as you get out to 30 and 40 years, the trend continues down. And once you get out to about 60 years, there's very few transformers that are being sampled, at least that were in this data set, that are above the age of 60. So Tony, of course, has some good knowledge of, he was telling me about some transformers that he's aware of that are over 100 years old that are still in good shape. But for the most part, this provides some valuable data. But as with any data, it's open to interpretation. And so again, Tony can talk some more about the statistics. Before we move on, Tony, did you want to add anything?
Yeah, sure. So this is an interesting chart in that it doesn't tell you anything about how many have failed. It only tells you the age of a unit in service. It doesn't tell you how long it lasted after that. It doesn't tell you if we've had 100 samples taken from a transformer. It just gives you an indication that there are fewer samples from older transformers, therefore older transformers are less likely to occur, which is what pretty much you'd expect. But the question is, why are there fewer transformers which are older? Some will have been removed from service, some will have failed in service, some will have been exchanged for larger transformers due for load reasons, etc. So we need to know why. And this graph doesn't tell us that. It just says there are more samples from younger transformers than older.
Okay.
Need a bit more to it to get that information. I would like to go back to something Moses said about qualified workers. And it is relevant here that to take a good oil sample, to generate data, to assess the condition of your transformer, and then make a decision about that transformer, needs someone who knows what they're doing to take a sample. And not only are they qualified to be on the site, not only are they qualified to take a sample, but when they take a sample, or they run an SFRA test, or they run a PD test, can they recognize data which is acceptable? Irrespective of how you interpret it, can you actually recognize that you've made a good reading before you try and work out what the reading means? And that to me is what a qualified worker is. They can identify an SFRA trace and say, yeah, it's what we'd expect. Now we'll try and interpret it. So just as an aside, thank you, Moses, for pointing that out.
Okay, so in search of more data on transformer life expectancy, Tony also pointed me to the C-grade transformer reliability study from 2015, which I found interesting. It's a C-grade report, C-grade primarily Europe, and this data set includes over 7,000 transformers from North America. And so I question why Seagrey doesn't have wonderful, lots of thousands of data points from transformers in Europe. But in any case, this is information that's publicly available, and so we wanted to include it in here. And I found it interesting that the graph actually ends at 65, and it doesn't show anything over 65. And again, going back to Tony's point, how many of these transformers failed in service versus how many were removed from service for various reasons. And so I went online and I found a couple pictures of transformers on the left. There's I'm guessing that these are similar applications, similar sizes. I don't have any real information on them, but looking at the picture, you might think that the transformer on the left is what you'd rather have on your system. It looks nice and new, and pretty colors on the bushings and so forth. And then you got the transformer on the right. So if you had that transformer on your right on your system, would you be inclined to replace it just because of the way it looks? And as Mo said, the presence of rust is not a good thing. But the real question is if you analyze the health of these two transformers and you understand the design practices and manufacturing practices of when these were built, we go back to the question of, does age matter or is age a significant factor? And today's transformers are built a lot different than they were 50, 60 years ago. And so the real question in my mind is, which one of these is really going to last longer? And so again, looking at the transformer health and understanding, based on testing and ensuring that you're looking at the right things on your transformers to understand, what's the real health and is there a need to change it out or not?
Yeah. If I could add something to that, Bill. Sorry, Leon. So to me, this is a useful chart, but again, it's not the full story, in that what we're looking at is a chart of the survivors, and we're looking at how old they are, but we don't know what life they've seen. We don't know how many faults they've seen. We don't know whether they've been supplied in. Is it northeast wet? Is it southeast wet with lightning? Is it west coast wet with high temperatures? Is it from another part of the world? What we do know is the age. Now, things, as far as I know, don't fail just because of their age. They fail because there are failure modes which exhibit themselves over time, and that time is going to be the age of the unit. For example, the number of through faults that we see on a transformer will increase not because the transformer is old, but because it's old and is in a particular area. The degradation of paper, which is a one-way process, that will result from temperature, from oxygen, from moisture. Those three things will act upon the paper over time. So the time by itself needs something to make the transformer deteriorate, and we call it aging, even though the age itself is not an indicator of whether the transformer is in good or bad condition. External rust, as you might see on the right-hand side, is definitely not a good thing, but it's far better than internal rust, which we sometimes see on transformers. And one of the questions I sometimes ask is that if I have a transformer which is 1 year old, looks a bit like the one on the left on the picture, and I have one which is 50 years old, looks a bit like the one on the right, and when I do a full assessment, they're in the same condition. If I had to choose one, which would I keep? And I would always say choose the 50-year-old one, because it's only going to get worse over another 50 years, whereas the first one was going to deteriorate over 1 more year. So after 1 year, it's lost a certain amount of its capability, whereas the other one took 50 years to get to the same point. So we have to be very careful about how we use age as an indicator of a problem. It's usually an indicator of a failure mode which acts over time. I'll stop there.
Thank you, Tony. And so
I can take this one.
Actually, yeah, I'll have you talk to this one as well.
So this is taken from an ISO standard, ISO 18095, which looks at power transformer, the components, and the failure modes. And the failure modes are really distributed into 4 counts. There's dielectric faults where the insulation can no longer take the voltage. There are thermal faults where the system can no longer take the current and dissipate the associated heat. Mechanical faults, quite often due to lots of inrush current when we weren't expecting that, lots of through faults which shake things up inside the transformer, loosen things, which make it a lot more difficult for the transformer to survive further mechanical input. And then things from external causes, lightning and so on. So there are 4 different types of source of failures on transformers, but we have to be careful because just looking at what failed doesn't tell us necessarily how it failed or why it failed. And on the right, we have some insurance company statistics, and we can see from that that quite a lot of these sources of failure are outside the transformer. Lightning, for example, it doesn't go into great detail, but the paper from Bill Bartley is useful. And if anyone's interested in a copy, let me know. The interesting thing now is that the different failure types are going to be affected by how well the transformer has been kept, maintained, how well it has been looked after. It's a classic thing. I had a Ford Focus car for 10 years. It worked just fine. I gave it to a significant other of mine. 6 months later, I needed a new car. Now, there was no difference in the roads it was on, but the way it was driven, how it was driven, et cetera, suddenly we need a new vehicle. So we've got to be very careful. It's not just who made it, when they made it, what life has it seen, but what life is it going to get in the future as well? What's it going to be subject to? And we are going to be subject to faults. We are going to be subject to deterioration, and it's how we detect those and manage them, which is important. Thanks, Neil.
Thank you, Tony. And so, well, Tony, I'll let you talk to this one too, because Tony, for years I've heard about the bathtub curve, and I've talked to customers about it, and based on information available in the industry, the life of a transformer is thought to, or the reliability, the failure rates of transformers are thought to be basically a bathtub curve. And so Tony kind of enlightened me to the various other things that Nolan and Heap had put forth. And so I'll let Tony talk to this.
So in the 70s, Nolan and Heap worked at United Airlines. They produced a seminal paper on reliability, and they produced the whole concept of reliability-centered maintenance, which really needs to have behind it an analysis of why things fail, how they fail, and what kind of failure rates you would expect to see. Do you have on the left-hand side of the chart? Now, each of these 6 charts shows time along the x-axis, and on the vertical, we're looking at likely failure rates. So the higher up, the higher the failure rates are more likely to be. And so the bathtub curve is the famous one. You have infant mortality, you go along with a random failure rate, and then you have a rise at a certain point in time. There's a wear out one, and they identified 6 different, I won't go into the great detail here. It's one where there's no, the random, where there's no initial infant mortality and there's no end of life, it's just random failure throughout. And they then worked out how many different asset types were governed by each of these things. Now, admittedly, they were working in the airline industry, different components to what we're used to. But in addition, we've seen this applied analysis done in medical industry, in the electric supply industry, in the mining, in oil rigs, and it's generally the same frequency, that the bathtub curve only applies to about 4% of asset types. And if you reference back to the C-grade paper, the C-grade technical brochure Leon mentioned earlier, within that they've got failures not just from the 7,500 examples from the US, 7,500 transformers, but we've got from more than a dozen different countries, thousands and thousands of transformers. And when you looked in total, there was no indication of a bathtub type curve. What is far more likely is to get the infant mortality and then random failures with a possibly you can see a fatigue element to it. Depends how you look at the data. But we've got to be very careful how we apply these, because normally people will say, what I find is people remember the bathtub curve and they apply it without reference to reality. I'll come back to that one in a moment, because there are quite a few places where we've done this and there isn't a far end to the bathtub. And it is quite possible that by the time you get to where you think that bathtub is going to start, the population you're interested in has disappeared because they've all failed for random means. So Does that cover that, Leon?
Yep. And then you get the next one too here.
So this is something I worked on with a colleague at Global Engineering, Dr. Hernandez, Ronald Hernandez. He's done a lot of work on a huge database of transformers and failures that we've looked at over the years. And what he did was he looked at individual companies, individual failure rates, how they changed year by year, decade by decade. So what I did was try and do a summary and say, for all the transformers that were built in our database from 1950 to 1959, what proportion of those failed in the first 10 years? What proportion failed in the next 10 years? What proportion failed in the 10 years after that? And so there's a light blue line towards the bottom of the chart. And you can see for those, there isn't much of an infant mortality, but over decades, there is a rise in that failure rate, and it's still rising when you get to 40 plus years old. So for the next decade in orange, a little bit further up, we can see the transformers from 1960 to 69 vintage. And we can see that in the first 10 years, there is a failure rate of about 1%. Then that rises so that in the next 10 years, it's higher and then rises again, as if that blue line has been moved to the left. Then you get to the 1970s, the gray line. And again, it's that rise in the first 10 years, next 10 years, and so on. And so what we're seeing is that the unreliability seems to be coming in earlier. And this has got nothing to do with individual manufacturers. It's got nothing to do with individual designs. This was just a general population. And a general thing to note is that those transformers built in the 50s seem to last a lot longer before they had some significant unreliability. Again, you move into the 80s, you move into the 90s, and that initial peak is getting sooner and sooner. But take it for what it's worth, that these are population, the statistics are for the population. And as ever, we always have to remember the statistics apply to the population and not the individual. So if I have a transformer from 1985, say, to work out what condition it's in, I have to go and look at that individual transformer. I have to go test and assess, gather the data, make decisions, analyze, work out what failure modes may be in operation, and then work out what the urgency of my intervention might be and how long I think this unit has. Likewise, if I have one from 1990 to 1999, I may expect the population to show that some of them will likely fail sooner. But to find out about an individual unit, I need to look at that individual unit. And that, to me, is the important message. Statistics are applying to the population, not to the individual. And as far as the car on the right, the DeLorean, who wants to return to the 1950s, certainly not me, because I recall that there were an awful lot of things that went wrong in the 1950s that just weren't very nice.
And we probably couldn't afford a transformer today if it was built like it was back in the 50s, since generally they were much, much larger.
Yeah, much larger, but probably still alive now and working.
Exactly, exactly. So one of the things, one of the big factors in transformer reliability is design changes. So as we have moved to a world of computer-aided design and the world of using slide rules, as far as I know, maybe Tony still uses one, but as far as I know, I was aware of slide rules when I went through engineering school, but I never learned how to use one. So, but what we do know is I spent 10 years in substation design, and I know when I was buying transformers in the 90s and replacing transformers, failed transformers when I worked at the utility, most of the new transformers were roughly half the size for the same rating as a transformer that it was replacing. And so we really didn't have an issue. The foundation was just fine to hold a transformer half the size. And so we never had to enlarge the foundation as long as we weren't actually significantly increasing the rating. And so the graph here shows how designs have changed significantly over the years. And I'm not sure this actually came from information from Herman Vogel at TJH2B, so another reference to TJ. So I didn't reach out to Herman to find out where this came from, but I found it very interesting to see in the early 1900s when we were starting to build out grids and so forth, very extremely conservative designs. And as things progressed, designs changed year over year after year. We saw the amount of oil per kV reduced significantly. And so the amount of oil today that's in a transformer compared to the amount that was even in the 60s or 70s is significantly less. So it makes sense that we're going to see transformers, since they're smaller, tighter clearances, more partial discharge, more susceptibility to manufacturing issues. So a manufacturing issue that may have not been a problem in the 1950s or 60s can cause a transformer failure very quickly today. And so, and maybe Tony has some data on infant mortality, but my feel is that, I was working with a utility that had installed a transformer or was replacing transformers. They're 60-year-old transformers because they were worried that they were going to be failing. And the new transformers, some of them failed on startup. And so you have to question, how long would those old transformers have lasted if they would have left them in service? And so I happened to be working with a customer, probably 10, 12 years ago, that had a transformer failure at a power plant. The picture on the right is a transformer that was an auxiliary transformer at a power plant, and prior to its failure had no history of problems. And you can see the point of me putting it on this slide is this was a 1970s vintage transformer. You can see how small the windings were in that transformer for how big the tank is. And so, of course, today's designs you wouldn't have near that much space. But the story behind this transformer was apparently they had some large motors that needed 2 transformers to start up, and 1 transformer was out of service. So they found out the hard way that, yep, you really can't start the big motor with 1 transformer. So I had never seen a transformer open up the tank like a door. So found that to be a very interesting case there. And then I'll let Tony talk about the complexities of some of the transformers today on the picture down below.
So just on the quantity of oil per kVA, note that the chart is not about voltage, but about the load going through the transformer. And the load will generate heat. So what the chart is telling us that the amount of heat generated is being cooled by less and less oil over time, which means it's going to have to be more efficiently used if we wish to dissipate heat like we used to. And that's one of the reasons why the famous Westinghouse 7 million series had problems, is that forcing oil through the transformer. It's a 1970s design, which they made smaller, but the oil got forced through the transformer and would pick up static charge as it flowed. And the 7 million series was famous for what's called static electrification. A bit like having a Van de Graaff. The oil would go through, it would go fast through some parts, it would pick up charge, it would deposit elsewhere, it would build up, then it would discharge and eat away the insulation. So we've got to be careful that we understand the chart as it relates to the cooling of the oil and the ability of the transformer to cool. Transformer at the bottom in the middle, that's the guts of a transformer after it had been taken away from site after it had failed. It was very difficult to inspect internally, but you can see the 3 main windings off to the left, and on the right we've got what's called the preventative auto, which helps regulate the voltage on the tap changer. And within that preventative auto, a brazed joint had come apart, and that had led to huge amounts of heat generated at the poor joint. And we had temperatures on the tank next to that in excess of 200 degrees C. That was a transformer we tested ad nauseam, to quote Leon from earlier, and we got lots of information, said we can't fix it on site, take it back. They fixed it, put it back in service, and away they went. So they are complex items, and looking at the size of that transformer, if you drop a small piece of copper, just a small piece of a penny, into that transformer, you can kill it without any problem at all, because there are certain places where it can go and it will just cause problems with the electric fields. So they are extremely strong under pressure, but they're extremely, what's the best word for it? Susceptible to problems as well. Yeah,
Delicate situation, right?
Delicate, yes. Take care of them. I must admit, I did feel a little wary earlier because Mose was talking about how often you should maintain transformers. And when I was at National Grid US, we said maintenance should occur at least once every 12 years. That's when maintenance becomes due. And it's not overdue until it becomes 15 years. So you've got a 3-year gap to do your maintenance. And once every 12 years for us was adequate, mainly for the transmission side.
Okay, so what are some of the maintenance strategies that people employ? And so we've already been talking about a number of different things today, and I thought it appropriate, based on Tony's comments about how what kind of life has that transformer seen. So I picked a fairly reliable, well-respected car, a Subaru, and yeah, would you rather have the one on top or the one on bottom? Of course, the Subaru on bottom isn't doing so well, and so your transformers are the same thing. If you're not treating your transformers properly, if you're not maintaining them, if you're not keeping the protection from letting the transformer see through faults, the more through faults, and especially the more significant through faults that they see, the less life you're likely to see from that transformer. So as Tony pointed out, through faults are a big issue, and protecting your transformers from through faults is very important. And so that goes back to, again, Moses' presentation about making sure your protection schemes, your relaying and so forth, are properly maintained. So what a lot of people like to do from a maintenance strategy is the do nothing strategy. There's lots of people that see transformers out there as a big gray box, and as long as it keeps humming, there's no issues. And so they really do not understand the complexities involved in that piece of equipment. And there's usually a lot of other things that are going on. So if you work for a utility, there's trees to be trimmed, there's lines to be built, there's storms coming through. And so again, if the transformer is not exhibiting issues, significant issues, then a lot of people kind of forget about them. And so being such a critical component, and one that's certainly harder to get, going back to Moses' presentation again, online monitoring is a great strategy to employ to have the transformer let you know when there's a problem. And so hopefully you can fix that problem before the transformer fails. And so what's very popular, as Mose also indicated, was that periodic insulating fluid samples. So we've moved away from the term oil sample as we move into alternative fluids, the esters and so forth. And so now we're calling them insulating fluids. And so taking those fluid samples, and typically people are taking those once a year, probably on average. Critical units, a lot of people will sample quarterly. Non-critical units, Tony, what do you guys see at the Doble Lab as far as typical oil sample times?
It depends usually on the MVA of the transformer, and anything which is considered 10 MVA or above would usually be annual. Some places we went up to 50 MVA and higher, and they would be annual or 2 yearly. So it depends on the individual organization and how risk averse they are and how well they understand the oil sampling process.
Right. And we were talking to somebody at a conference recently that was saying at least their labs, they're currently looking at 30 to 90 day lead times to get analysis back. And so in some of their, they've got, this customer had some high industrial lighting loads that were generating lots of harmonics and failing like 2 MVA transformers after a couple of years and so forth. So they said in some cases they've seen where otherwise last year's sample looked fine. They took an oil sample, and before the sample came back this year, the transformer had already failed. And so these are typically, that's not going to occur, but it's a concern when they actually indicated that when they tried to rush a sample at one of their labs, it's a transformer service company, and they said they used several labs. It still took like 30 days to get a rush sample back. So I'm not sure if people are just taking more samples today, if it's harder to, if labs are dealing with various things, but these are certainly today, again, getting qualified employees and getting the job done, it's more difficult to do than it was a few years ago. So again, online monitoring, people deploy all kinds of different monitoring, single or multi-gas DGA monitors, monitoring your current voltage harmonics, bushing monitoring, partial discharge monitoring, LTC monitoring. So there's lots and lots of monitoring available today. And as Maz has pointed out, it's very important that you not only maintain your transformers, you also maintain your monitoring systems. And that if the monitoring system is telling you there's a problem, you need to do further analysis to understand what's going on. And do you have any more to add to that, Tony?
A few little things, if I may.
Sure.
3 main reasons. I used to say 2, but the 3 main reasons people apply condition monitoring. I always used to say 1 was to learn about the asset, whichever one it is, breaker, transformer, cable. 2 was to learn about the monitor and what it can do for you. The third reason I put in these days is because people apply it and then don't benefit because the organization is not ready for it. So the third reason to apply it is to work out whether your organization can actually manage it. Related to that is feedback. Usually I quote a guy called Don Schubert, Marsh Insurance, but I've heard similar from HSB, from FM, and that condition monitoring is a symptom of good asset management. People who apply condition monitoring with forethought as part of a process where they've got action plans all set up, they tend to be good at the asset management and they use it to support the job they do. If you just apply condition monitoring, that doesn't make you a good asset manager. That just makes you someone who's applied condition monitoring, and it isn't necessarily going to help. So those would be related to that. Then comes the whole approach of online monitoring, whether you're looking to do detection or diagnostics. And as you could well imagine, there's a cost differential, and it is sensible to work out why you're doing the monitoring to start with. And don't expect to put lots of condition monitoring on and suddenly be able to do everything. You need to be thinking about how the organization responds to it. I think I should stop there, otherwise I'll talk too much.
Yeah, you actually stirred a couple thoughts in my head there, Tony. So one of the things that I've been doing online monitoring, different types for the last 15 years or so. And one of the things that online monitoring has told some customers is that they have problems that they weren't aware of and they're not prepared to deal with. And so that's another thing that you need to be considered is the level of commitment the organization has to actually do something about it when you identify a problem. And so, of course, some organizations that's harder than others, and it goes a lot to what Tony was saying about the sentiment in the organization, and what people are prepared to do in the event that the monitoring identifies an issue. And so, again, assessing those risks and so forth. People usually go back to the vendors and say, what is this really telling me? And of course, folks like Tony are always there to provide their level of experience and so forth. So on the fourth point here, the solutions depend on criticality, health, operating history, et cetera, et cetera. So typically small, healthier, non-critical transformers may get something like a hydrogen monitor or hydrogen and moisture monitor only. Usually monitor when people start doing monitoring, the DGA monitor is the first thing they'll put on, because looking at the insulating fluid and when gases are generated in that fluid is a good indicator, just like a blood test on yourself is good to get an understanding of how healthy you are. Looking at the gases in the transformer oil or transformer fluid are very important. And then of course, as the criticality increases, or you may have unhealthy transformers on your system, whatever the case may be. Of course, there are times when certainly you want to go to the multi-gas systems that, do partial discharge and bushing monitoring and so forth. And again, the vendors can provide a lot of recommendations on what you should be putting on a particular transformer based on what bushings are in there and what type of low tap changer, if it has one, and so forth. So for our conclusions, I did a search for happy transformer, and apparently there's a cartoon out there named Happy Transformers. So we all want to have happy transformers. And so when I went out to find data on how long your transformer is going to last, it was very difficult to find industry data on that topic. And we did want to put this together and present the data that is available so that people can have a little bit better understanding. But it all goes back to how good your crystal ball is. And everybody expects the asset manager to have a crystal ball and be able to tell them, well, when is this transformer going to fail? Or is this a serious issue? And it's also important to note that a lot of people are focused on transformer failures, but a lot of people, for various reasons, you take transformers out of service for various reasons, not just for failure. So they may be upgraded, they may be, people are concerned about the age and so forth. But again, from the data that we found, age isn't necessarily an indicator that you should be replacing your transformers. Typical life expectation, if you look at the data we have, it looks like the amount of transformers that are, you start after 20 to 30 years, you start seeing less and less of those transformers. I saw a recent article that a certain class of transformers, utility was changing them out every 20 years. And in certain parts of the world, like Japan, they are very, or at least in the past, have been very rigid about changing out transformers after a 20 or 30 year life. And so the concern, of course, is the transformer you're putting in to replace it going to last as long as the old transformer would have lasted if you would have left it in service. And so I like to say that your transformers will likely last a long time if they're designed well, manufactured well, maintained well, operated within recommended guidelines, again, minimizing through faults, and so forth. And I know Tony has some additional things to say here.
You're very prescient. So first question is, what is a transformer? And the reason I asked that question is that we can maintain certain parts of it by just replacing them. Bushings, for example, if they deteriorate, we can put new bushings in. The cooling system, if it deteriorates, we put a new cooling system in. But the main windings, that's not something that we can replace easily. And our transformers are not commodity items. They're all different. They're all handmade chemical baths. And they're all subject to the problem of being a non-commodity item. But imagine you take it away from being transformed. You just look at your car. I always like the cars. So your Subaru. If the tires start to go down and start to show evidence of a leak, that's going to be a problem that if you do not fix, you may have to replace the whole car. If the brakes are starting to fail, that's something you need to fix before you have to replace the whole car. So you've got to be thinking in terms of what can we do to maintain? And maintenance is just a management of deterioration. Maintenance is about checking, inspecting, gathering data to see if things are getting worse that I can fix. So where would we start with the age of the transformer? First of all, if it's a new transformer, did we specify it well? And the second thing would be, are we factory witness testing it and then checking it's being shipped correctly, installed correctly, put in place? Little things can be bad. And we have had a transformer fail recently where they had undersized the leads from the bushings, what's called the RV lead earlier, to the windings, and they were failing in service. This should have been picked up at the factory inspection test. Well, let's look at the rest of the population. And for each of those, we need to treat them as an individual. For each transformer in our population that we're interested in, we have to collect data. We have to analyze the data and then see whether there is any failure mode in operation. And then consequent to that, how much life has been lost from the capability of the transformer. Monitoring allows you to update that more frequently. Monitoring allows you to detect both long-term failure modes and short-term failure modes. I could discuss bushing failure modes. GE type U's usually go bad over several weeks to months. Trench COTs, trench coaters, usually over a period of a few hours. And we have cases where we can show that if you monitor sufficiently well, you can detect and avoid failures. And that includes for detection using DGA, such as hydrogen monitors. So question is, on day one, I've got 100% of the life left of my transformer. And I would estimate for a good transformer, that would be 60 years. That should be what I would expect to be a minimum. And we then have to vary that depending on how we drove the transformer, what faults it's seen, what maintenance it's seen, what overheating it's had, whether it's been dried out, etc., etc. And that has to be added in. So to me, on day one, for a well-specified, well-built transformer, I want at least 60 years. And it's going to reduce from that depending on what I've done with it. Back to you, Leo.
Okay. I think that's the end of our presentation. Are there any questions, Randy?
Yeah, good. We have several questions, so if we could get short answers, that would be best.
Yeah,
Regarding, let's see. Regarding online monitoring, what are the alarms and failures detected by you at present? Is there any statistics? Are there any statistics from? I don't know how to get rid of that. Are there any statistics for online monitoring of the faults and alarms detected? What type of faults and alarms are they?
Okay, so there's about 16 hours of so in general, again, depending on the criticality of the transformer, you're going to install monitoring appropriate for for the criticality of the asset, and most of the time the value of the transformer is very small compared to the process or the revenue at stake if you lose that transformer. And so most utilities, large transformers, are installed with redundant systems so that if one fails, others in the system can pick up the load. But as you move farther and farther down to the distribution and so forth, that may or may not be the case. So again, what's monitored and the alarm set points and so forth. If you're looking at a hydrogen monitor, or bushing monitoring or partial discharge monitoring, that's where you look at the standards and you look at the suppliers of the monitoring equipment for recommendations on those alarm points. Anything else to add?
Right.
Yeah, if I may, just briefly, if you look at IEEE C57143, it'll tell you what you might want to monitor on different parts of a transformer, but it won't give you limits as to what you should set. And same reason why we don't have common limits for tire pressures on a car. Different manufacturers' tires will have different limits. So you have to understand your own individual transformer application for bushing monitoring, for partial discharge monitoring, for temperature monitoring, for dissolved gases monitoring. And the data you generate from the monitor should help identify the most common failure modes. Other statistics from monitoring about faults and failures detected. Yeah, we can tell you about trench bushings. We can tell you about GE type U's. We can tell you about Westinghouse 7 million transformers. We can tell you about Westinghouse O plus bushings. Lots of different bushings have individual failure modes, and detecting those is not difficult. There are some failure modes now we get with delaminations in resin fill bushings, which are a little bit more difficult. You have to add partial discharge to detect those. So the type of faults reflect the failure modes, and the alarms should be there to give you enough time to do something, which we normally do. We do know people who use the monitoring just so they can say, yep, that one's going to fail, and they let it fail. It depends what the transformer is and what the problem is.
Right. It's also important to note, Tony just talked a lot about bushings there. Bushing,
DGA, I love DGA, sorry.
Well, bushings are a common failure of transformers, and it's important to note that when people monitor the oil or the fluid in the main tank, the bushing can fail regardless of what the oil in the main tank looks like. So bushing monitoring is becoming more and more popular, and for, you know, as Tony pointed out, there's a lot of reasons for that. One of the interesting things that we found at H2 Scan is in China on 750 and 1000 kV bushings, there's actually a tap where you can take an oil sample from the bushing itself. And so China State Grid has been installing hydrogen and pressure sensors on those taps to monitor the real-time hydrogen, if hydrogen is being generated, and at what pressures, what the pressures are in the bushing. So again, depending on the equipment, most bushings don't have that capability. So, you know, you got to look at what your equipment is and what's available, and then understand, you know, where you should be setting those alarms.
Okay, great answer. Thank you very much for the presentation. We have to move on.